Hello, welcome to the summary session of this NPTEL Points of Topology course. So, yeah, so this is Shavik and what from Spashinam. So this is the last and final session of this course. It will be 1 hour. Okay? Sorry, it will be 1 hour session only. Okay, okay. So first, if you have any problem or any doubt from previous session or any doubt related to this course, you can ask me now, or you can drop an email to me, and I shall get back to you as soon as possible. Okay? So if you have any problem, then I can start with, or else let's first start summarizing the sessions that we have done. That we have. Let's first summarize the concept that we have done. Okay. So let me write it down. One. Can you please confirm whether I'm audible and the screen is visible to you or not? Well, so let's start our today's session. So what we have the concepts learned till now? Well, one thing you should notice that there are many things we have learned, including some things, including some non-special. Okay, but those does not come from the big topology portion. Okay, so let's so from topology point of view, the things are as follows: compactness, connectedness, separation axioms, co-discountability axiom, five is uh, okay, five is uh, five is topological dimension. Okay, six is topological groups. So more or less, these are the concepts that you have learned, and there is something called non-linear spaces. So these are more or less the concepts that you have learned. So Avinash send one just for you. Let me let me let me go through it towards the stage. Okay. So the question is that can you please explain why circle and hyperbola are not okay. Okay. So okay. As per your look, why hyperbola circle not homeomorphic? Why? So this is the circle, this is one, and this is hyperbola. Um, this is hyperbola. Now, why not homeomorphic? Suppose F is a homeomorphic, B. Kindly hold a minute. I shall get back to you. Hello. So, the question that you have asked is the so basically, sorry for the inconvenience. There is electrical issue, so that's why we try to fix it out as much as possible. Anyway, so the question that of asks the hyperbola circle under suppose if we have homeomorphism between them. Okay, so this implies what? F of circle minus point is homeomorphic with. I mean, anyway. So firstly, of okay. So first of observe is that circle is a connected. Okay, circle is a connected, but this hyperbola is disconnected. So this tells circle is connected, but the hyperbola is disconnected. Okay, so this tells that circle is not homeomorphic to hyperbola. Why? Because if they are homeomorphic, we know that for homeomorphic things, then continuous. I mean, if two things are homeomorphic, then there's. I mean, so look. So it's under the continuous map, homeomorphic. Um, so under under continuous map, connected space goes to all maps to all it connected. That is, x connected implies f of x connected. Okay, so since here circle is connected by hyperbola disconnected, that's why f of s1 cannot be equal to whole of hyperbola because circle is connected by hyperbola disconnected. So that is the argument. Okay, Avinash. Okay, now. Okay, so do you have any more problem or any more question? Okay, okay, okay. So now, hmm, okay, so first look at compactness. So in compactness, there are many things like compact implies connect. I mean, so okay, so compact means any open cover is a countable sub. Sorry, any open cover is a finite sub cover. The compactness there is a weakened notion compact namely in the Laplace. Any open cover is a countable sub cover. Connectedness means any open cover. Uh, connectedness means any if a X space is it's be connected, the only set which are both open and closed in X are connected. Okay. And separation axioms and counter separation axiom contains Hausdorffness, normality, regularity. Countability contains first countable, second countable. And then it is topological dimension. Then there is something known as topological group. And in between we have done some non space. Okay, but let's not get into this. Okay. So in between compactness, the what is the main important fact? Main important fact is in Hausdorff space, compact implies closed. And any continuous maps and compact space to compact. Any continuous maps and connected to connected space. Okay. Then separation axiom means Hausdorffness, sorry, regularity, etc. Okay, then we have we have also seen Pete's extension theorem and Ulishan's lemma. Okay, so this is a very interesting fact we have seen. Okay, so now tell me one thing. Okay, so now let's discuss some problems regarding homeomorphism. Okay, so first question is that show that circle and ellipse are homeomorphic. Circle and ellipse are homeomorphic. So that is what we need to show. So basically, this is circle and this is the ellipse. Now these are homeomorphic we need to show. Okay. So what we actually one minute. So what we actually need to prove is the following. Circle ellipse of homoeomorphic we need to show, right? So, hmm. So basically, so look, now observe is that if we take circle and if we stretch slightly from the both side of the circle, it will become a ellipse, right? And vice versa. But okay, so that's why we can directly say it's homeomorphic. So, but mathematically, how to show they're homeomorphic? So basically, what we need to do, we need to construct a function f from a circle to ellipse. Let's take the equation of the ellipse to x squared y squared x squared by a squared plus y squared b squared 1. Okay. Now we need to find a homeomorphism between these. So what we are making is the following: xy goes to ax comma by. This is f, and so f inverse will be what? Xy goes to x by uh, a comma y by b. Okay. So of course, so these both are continuous assignments. These are continuous assignments. These both are continuous assignments. So this tells that these are homeomorphic. F is homeomorphic. So this is the one way of doing this problem. Okay. Now suppose now there is another thing. Sorry. Suppose this is some x and this is some y. Okay. And suppose if we have a map from x to y. Okay. And suppose this is the graph of it, right? Now Now observe that this graph of x and x are homeomorphic. We can just push it down, right? So now the next theorem is that show that if let f be continuous, f be continuous, then show that graph of f is homeomorphic to x. Okay, how to prove this? So basically what we need to construct a function from x to graph of x follows. How x going to x comma fx and And here, what we're doing, x comma y equals to x. Okay. So these both are continuous assignment. So this tells that, so this tells that, so this tells, so this tells x is x homeomorphic to graph x. Okay. Okay. Now, uh, what- now, so okay. So now the next problem is as follows. Uh, Um, okay. So, what? Um, so, so, so the next question which just follows. Okay, so these questions are quite important. This might come in exam also. Okay, so this question is that show that any infinite set with co-countable topology is not not compact. Sorry, cofinite topology. Any infinite set cofinite topology is not compact. How to do that? So, well, so this question is basically a repeat question, but this question is quite important. Argument is also quite important reference. But okay. So, so the argument goes as follows. So, so let X be infinite set with cofinite topology. Okay. Sorry, infinite set of always compact. Let U U alpha be an open cover for X. Okay. Be an open cover of X. So, uh, so X minus U alpha is finite for alpha. So choose an alpha naught from the index set. Okay. Then X minus U alpha naught is finite. Okay. So that means u alpha naught. So let that set be x1, x2, dot xn. Okay. Now, so let xi belongs to u alpha I. These numbers x equal to u alpha 1, u alpha 2, u alpha n, u alpha naught. So this tells that this open cover U has a finite subcover. So this tells that this U has a finite subcover for X. And so this implies what? So this implies X is compact. So this implies X is compact. Okay. So this way we can show our I mean asked to repeat. Okay, so anyway, I'm just repeating the argument already. So let me repeat the argument here. Okay. So so suppose X is an infinite set in cofinite topology. Suppose X is infinite set in cofinite topology. We need to show that F is compact. X is compact. Okay. For that, what we need to do, we took some open cover of X. So that is call it U is equal to U. I mean open cover of X. Okay. So X minus equal to finite for all alpha. Now we can choose a alpha naught belongs to from the index, right? Okay. That X minus U alpha naught is finite. Let xi belongs to u alpha I. So these implies what? These implies x equal to u alpha 1 union union of u alpha n. These implies u is a finite subcover for x. So this tells what? This tells that x is compact. So this is the argument follows. Okay. Avinash, please let me know. Do you understand? Or or any confusion from the previous statement or this question? Let me know, Avinash. Do you have any question or doubt till now? Or is there any issue that's in the solution itself? Okay, thanks, Avinash, for the response. Okay, so now let's go to the next question. Okay, so now the next question is as follows. Show that any uncountable set with co-countable topology, show that any uncountable set with co-countable topology is not compact. Uncountable set with co-countable topology is not compact. So So, so let X be an uncountable set with co-countable topology. Okay. So, since it's uncountable, so choose the countable subset of X. Well, so this argument, the previous question argument, these are quite tricky. So you need to practice
Can
a
I repeat
lot.
the previous one?
Okay, Mustaq. So okay, okay. So okay. So let me repeat.
Hello.
Yes, yes. Am I audible?
Can you please have this one? This one.
Yeah. Okay. So. Huh. So, in the previous question, we need to show that any infinite set with cofinite topology is compact. Okay. So this wanted to show. So for that I had started with some open cover of X, and we need to show that that U has a countable finite subcover. Okay. Now since we're in cofinite topology, so X minus U alpha, so X minus U alpha is finite for all alpha. So then we are choosing an alpha naught from the index set. So this implies what? X minus U alpha is finite. So then, so let that be x1, x2, dot, dot, xn. Okay. And let xi belongs to u alpha. So this implies x equal to u1, u alpha 1, u alpha 2, u alpha, because this contains all the xi and the rest of the portion are inside u alpha a. So this says that u has a finite subcover for x. Okay. So this is the argument. You understand? Mustaq, you understand?
Yeah, yeah. Yeah.
Okay.
Okay.
Okay. So now let's go to our next question. We need to show that any uncountable set count. We need to show that any uncountable set with co-countable topology is not compact. Okay. So, so here we are choosing an so here we are choosing an uncountable set. Now we are choosing a countable subset. Sorry, choosing a countable subset. We are so here we are choosing a countable subset of X. Let it be x1, x2, dot, dot, dot. We need to now look. We need to show this is not compact. Means we need to construct an open cover which does not have a finite subcover. Correct. So choose U is equal to U alpha such that UN is equal to X minus Xn plus 1, Xn plus 2, Xn plus 3, dot, dot, dot. Okay. So this UN forms an open cover for X. Okay. Now let it admits finite subcover for X. Let X equal to UN1 union UNK. Now put M is equal to max of N1, N2, Nk. So this then, but Xm does not belongs to UN1, union UN2, union Ank. So of course, X cannot be equal to union of UN1, union of UNK for any such collection, for any N1 into N. So this tells this open cover U does not admit finite subcover. This tells this tells um, X is not compact. So let me repeat that. So let X be uncountable, so co-countable topology. Okay. So we can choose a countable subset of X, call it x1, x2, or xn. Okay. And un is equal to x minus xn plus 1, comma xn plus 2, comma xn dot dot dot. Then un forms an open cover codex, and it admits a finite subcover codex. Okay. Suppose it admits a finite subcover codex. So then x equal to un1 dot dot union un. Now we are putting m is equal to max of n1 comma n2 dot dot n. But xm then does not belongs to union of un1, union un2, union un. For any n1 and n2. So this tells that the open cover E does not admit a finite subcover. So this tells that X is not compact. So this is the argument. Do you understand?
Yeah, yeah.
Okay. Now, yeah. Okay. So now let's recall the statement of Wilson's lemma. What this tells? What this tells? This tells that let F be a normal space and A comma B are closed. A comma B are closed subspace of X. Then here exists a continuous function f from where to where x to 0 1 such that f of a fully equal to singular 0 and f of b fully equal to singleton. Okay, so this is what the vision demands. Now, okay, so the topological proof is quite different, but let's not get into that. So 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 let's so let's look into the proof for the metric space. Okay. Okay. So proof of Newton's lemma in metric space. So proof of Newton's lemma in metric space. Okay. So the proof is quite simple. So we have some AB. So look, any metric space is normal. Okay. We have already seen. Okay. So let A, B be two closed subspaces. of x. And defining f of x to be dAx divided by dAx plus dBx. Okay. Then clearly for x belongs to B, dx equal to 0, which implies fx equal to 0. And for x equal to A, dbx equal to 0, and this implies fx equal to 1. And for others, x, for other x, of course, d 0 greater than dAx less than dAx plus dbx. Okay, so which is less than 1. So the division is less than 1. So this is the so this proves Newton's lemma in case of metric distance. Okay, there is no harm in it. So well, so the topological proof. So the topological proof is for the metric space. So this is one very important thing. And there is another important thing, namely Fields extension theorem. So there is another thing in Fields extension theorem. So what does this? So here also X be a normal space. Okay, and A, B. To close our spaces. Okay. Okay, sorry, only A be the closed R space. Okay. It's a closed R space. Now, then any continuous map, yeah, from A to close 0, 1 can be extended to whole of X. Any continuous map A from A to close 0, 1 can be extended to whole of X. Okay. So this is what uh, is a deep extension. So now point is that Fields extension theorem implies recency lemma. How? Well, till now we have only discussed. Now let's uh, go with some ratios. So let A be two closed subspace of X. Okay. Define F. So and we're defining a map, yeah, from A union B to 0, 1 by whole in I'm sending the whole A to 0, I'm sending whole B to 1. Okay. Then of course, it doesn't matter. So then by keep the extension theorem, if can be extended to F delta from X to 0. And then F delta satisfies desired property. So this is the argument. Okay. So till now, is everything clear or any doubt or confusion till now? Please let me know. Okay. Okay. So now, so now, so okay. So now, let's go with something known as retract. So well, so this the retract thing is actually not a direct part of quantum topology. It somehow comes under some other things. But as per the definition of the retract, it comes under quantum topology, so that's why we can go through it. Okay. Now, so so what is retract? Let X be a space and A be a closed subspace. Then A is said to be a retract of X if here is the continuous function R from X to A. So the R restricted to A is equal to identity of A. Okay? If this happens, then R is said to be retract of A. Okay. Huh. So so now look, well, so this is a retract. Now one may ask whether D whether S1 can be retract of this column. One marks is a question, okay. But as yesterday we have discussed, this type of questions are not fully the product of concept topology. Somehow these things are connected with the algebraic topology, and particularly in particular, this problem cannot be solved with concept topology. For this, one has to go through algebraic topology and all this. So that's why we can. I mean, so anyway, I mean, this type of possible will not come. So, but whenever you need to issue something retract, so then what you need to? You need to construct a function, construct a function from that space to x that such that is directed to one. So show that R n plus one minus zero. Show that Sn is retract of Rn plus one. This is what we need to show. Sn is retract of Rn plus one. Okay. So okay, so that is what need to what you need to construct a from Rn plus one minus zero to Sn, right? So that a raised to Sn is equal to Rn to Sn. Just take few minutes, think about it. How to construct such a I should have back in a few minutes. Well, so okay, so one minute, let's look at the final note. Yeah. Okay. So Okay. So, so, so tell me, how one can construct a function a from Rn plus 1 minus 0 to Sn are the restricted to Sn is identity. What are the possible ways to construct such a function? Okay. So, so there might be many different, but one possible way is that f of x defining to be x by not x. Okay. So clearly, if restricted to is 1 is equal to identity. Okay. So this is one possible to construct this level of maps. Okay. So, but now one may ask, is open 01 a retract of real line? I mean, so look, so if suppose one, so suppose if R2 open 01 via retract, but that's impossible because if we take 1 by n that goes to 0, then f of 1 by n goes to f of 0, and f of 1 by n is the 1 by n, 1 by goes to 0, this nameless what f of 0, 0. But 0 does not belongs to codomain of f, right? So it so this so it's bizarre. So f of 0 is equal to 0 is a bizarre situation. Correct? So so this tells what? This tells that in so this tells that in Hausdorff space its retract is always closed. In Hausdorff space its retract is always closed. That's what it tells. Okay. So now, so how to prove this? Hausdorff space, Victor always goes how to prove. So, so let A be a retract of Hausdorff space. Okay. Now we want to show A is closed. How to prove this? So let we are taking a point x minus. Okay. So these implies one Rx does not belong to A. Otherwise X belongs to A. Okay. Now this states that there exists an open UV containing Rx and containing X as that U intersection V here. These two things together tells that X belongs to R inverse U intersection. Now claim is that R inverse U intersection V subset of X minus A. Because if T belongs to R inverse U intersection V intersection A, this implies RT belongs to U, T belongs to V, and T belongs to A, and then T belongs to A, RT belongs to U, together gives RT is equal to T. This implies T belongs to U intersection V. Okay, and this implies what? U intersection V empty. But that is not possible because by your choice, U intersection V cannot. By our choice, U intersection V is empty, but here it is coming into the non-empty. So that is a contradiction. So that's why. uh, So this says that R inverse U intersection V is subset of X minus A. So this is an open set. This implies what? This implies X minus A is open, and this implies what? This implies A is closed. So this is the argument. So let me repeat that. We need to show Hausdorff space retracts all S. Okay, how to prove this? To show A is closed that X belongs to A minus. So then Rx does not belong to X. Otherwise, X belongs to it. Okay. Now, so there exists an open set U and V, so that U intersection be empty. And this implies X belongs to R inverse U intersection V. Now, claim is R inverse U intersection V subset of X minus A. Proof is that if T belongs to R inverse U intersection V intersection, and this implies RT belongs to U, and T belongs to V, and T belongs to A. And RT is equal to T. This implies T belongs to U intersection V. This implies U intersection V non-empty. So R inverse U intersection V subset of X minus this implies X minus A is open, and this implies X minus closed. So, so basically, this argument is nothing but express playing with the definition house roughness open closed. Okay. So there is nothing really much complicated. Okay. Okay. Now, um, okay. So now let's go to the next problem. So the next problem goes as follows. Uh, okay. So wait. Um, okay. So okay. So Avinash asked to repeat this argument. So let's repeat. So basically, what we need to show that in a house of space, retract is always its closed house. Okay. So how to prove this? So suppose A be a retract house of space. Okay. And in order to show A is closed, we need to want to show A is closed. Okay. So let X belongs to X minus. So this tells that Rx. So 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 take X belongs to X minus. So basically our target is to show that A is X minus A is open. Okay. So so then so then Rx does not belongs to X. Rx not sorry. Rx not equal to X. Otherwise X belongs to A because the definition of R the codomain is capital. So Rx cannot. So there is the open set even V containing both Rn and X such that U intersection be empty. Okay. So this implies what? Now also this is one thing, and this implies that this Rx and X belongs to U and V, so X belongs to R inverse U intersection V. Okay. Now claim is that R inverse U intersection V substitute X minus A. How to prove? If R inverse U intersection V, so this tells that if T belongs to R inverse U intersection V intersection A, then RT belongs to U. And then T belongs to V and T belongs to A. Just because, I mean, this if intersection non-empty, then we can have some T at least one such that T belongs to R inverse U intersection V intersection. This means RT belongs to U. And this means RT is equal to T. And this implies T belongs to U intersection V. So R inverse U intersection V subset of X minus, and this implies X, X minus A is closed. And X minus A is open, this implies A is closed. Okay. So this is the argument. So okay. So I hope this argument is clear. Uh Abhinash, can you please let me know whether this argument is clear to you or not? Okay, thank you Abhinash for response. Okay. Uh so if you have any look. So okay, so let's stop here. So you have hmm, so so after now, so few days you have the exam, okay? So don't panic. Just go through the things that we have seen in the live sessions and we and the serve what we have done. Okay. Try to practice the assignment as much as you can. So practice the assignment as much as you can. And also to go through the previous concepts and outline sessions. Okay, and also one more thing, note that since this all the session is recorded, so you can go through the session later on to go through the discussions. And if you have any doubt, you can drop an email. I shall get back to you as soon as possible. Okay. And one more thing. So today the problem that we have discussed is not complicated at all, but the point is you need to practice a lot to get a grasp about this type of problems. Okay. So so this is the thing. Okay. So okay, one more thing is that in exam there will be objective questions also, subjective question also, and there in the exam, final exam, there will be no negative marks, so you can easily go through that. Okay. And one more thing is that in exam, if some questions comes regarding the homeomorphism, suppose we have seen in the today ellipse and circle homeomorphism. So I mean that can be seen directly, but it's quite difficult to prove. Okay, so in this type of situation, on Mr. Problem, try to prove this as much as you can. Okay, so or at least if it is not possible to prove mathematically, try to give some kind of argument, like we have seen that for a circle and ellipse, if we for circle and ellipse, if we stretch the circle, then it will be ellipse. Okay, this kind of technique you can write the exam. I understand this is a mathematical, but anyway, something is better than nothing. Okay, in that point of view. And when you need to show something is not compact, sorry, something is not uh, homeomorphic, you can first try to remove some points, and then mostly the problems that we given exam will follow like this. Just remove a point, you will get the answer. Okay, so that is the thing. So okay, if you have any doubt, you can drop an email to me, or also ask right now. So all the best for your upcoming exam. So this is the last session. All session uploaded in the website, and you can also see the assignment and the answers. So all the best for your upcoming exam. So I am leaving the session. Thank you all for this making this session awesome. I am leaving.